Hello dear friends, myself Professor Juned.N.Bhojawala welcome you all for our another lecture, that is Fluid Uncovered Part 3. In this topic we will be dealing about fluid kinematics, its fundamentals and flow analysis. A comprehensive exploration of methods and principles governing the fluid's motion for engineering students. The content has been structured to reflect the core topics which are outlined in major UG courses. Myself, Professor Juned.N.Bhojawala, working as Assistant Professor in Government Engineering College, Dahod, Gujarat. Before starting of the lecture, I would like to thank my principal sir, Dr. K.B. Judal sir, my head of department, Dr. Paresha Bharia ma'am, and my all the staffs and colleagues who have motivated me for this lecture. Now, let us start our session. Before starting of the session, let me give you a disclaimer that this presentation has been prepared using various multiple sources, including standard textbooks, reference books, publicly available materials which are online. Every effort has been made to ensure the accuracy and reliability of the content. However, unintentional errors may exist. Artificial intelligence, that is AI tools, have been used to assist in organizing, summarizing and presenting the material. Some images, diagrams and illustrations have been sourced from the internet and are used for educational and explanatory purposes only. Other images and visual contents have been generated with the help of AI tools. Proper credit is acknowledged wherever possible. However, if any content is unintentionally uncredited, it is purely coincidental. The primary intention of this presentation is to support understanding, revision and knowledge enhancement. This presentation is intended solely and exclusively for educational purposes only. So now we are here to understand what is fluid kinematics. So fluid kinematics is the branch of the fluid mechanics that describes the motion of the fluids. It describes the motion of the fluid without considering the forces that causes the motion. It focuses on geometry of fluid motion, how fluids move, wherever they go, and how fast they can travel. Unlike fluid dynamics, kinematics treats the motion as purely geometric problem. Why we have to study fluid kinematics? So to predict the flow patterns in complex geometrics, analyze velocity and acceleration in the fields, design efficient hydraulic systems, optimize aerodynamic performance, understanding mixing and transport phenomenon, validate CFD simulations, interpret experimental flow visualizations and many other. So it serves as the foundation for advanced fluid mechanics, its analysis and enables engineers for these various said purposes. Now what are the methods of describing fluids in motion? So one is Lagrangian method, which can be known as particle tracking method for our understanding. In Lagrangian method, we follow individual fluid particles as they move through space and time. We track their position, their velocity, their acceleration, their temperature, their pressure for each specific particle, like attaching a GPS tracker to a drop of water from where it originates to where it goes. A daily life example is ink in water. If you drop ink into water and track one tiny particle it moves, then it is an Lagrangian approach. Second example is raindrop. Tracking a single raindrop from cloud to ground is Lagrangian method. Third is tracking a car. Following one specific car movement on Google Map is similar to Lagrangian description. What are its applications? So some of the applications are tracking pollutants in the river or air, weather balloon tracking, ocean current particle simulation, blood particle tracking in biomedical studies, spray and combustion modeling. The key idea or the key parameter is follow the particle. Another method is Eulerian method, which is known as field description method. In Eulerian method, we observe what happens at a fixed location in space as fluid flows through it. We do not follow particles. Instead, we measure velocity at fixed point, we measure pressure at the fixed point, we measure temperature at the fixed point. Think like placing a sensor at one location and recording data continuously. So daily like examples are water flowing in a tap. If you measure the speed of the water at the tap outlet, you are using Eulerian method. Wind speed station. A weathering station measuring wind speed at one location uses Eulerian approach. Third is river monitoring station, measuring water flow at the bridge without tracking individual water molecules. So applications are weather forecasting models, river discharge management, wind tunnel experiments, air pollution monitoring stations, and computational fluid dynamic simulations, which is CFD. The key idea is observe at fixed point, do not track the particle. So here is a small comparison of Lagrangian method and Eulerian method. Focus is on individual particle, here location is fixed. Motion tracking is there in Lagrangian, Eulerian method no motion tracking. Mathematical complexity in Lagrangian is high, easier for large systems in Eulerian method. Common for particle simulation, common for weather models and CFDs. Examples is tracking a leaf in a river. Here Eulerian example is measuring river speed at a bridge. So easy way to remember, Lagrangian, look at one particle, Eulerian, examine one location. I hope this clears your basic fundamentals about Eulerian method as well as Lagrangian method. Now let us see types of flow. So uniform flow and non-uniform flow. When the velocity of the fluid does not change with respect with position at a given instant of the time, the flow is called as uniform flow. So velocity does not change with position at a given instant of time. Example, water flowing in a straight pipe of constant diameter. Non-uniform flow. When the velocity changes with position, it is called as non-uniform flow. So del V by del X in the above case is equal to 0 uniform, where del V by del X is does not equal to 0. Example, river flow, velocity differs at center and near the banks. Here the uniform flow and non-uniform flow is shown. I hope it is clear to you. Constant velocity across all the sections in uniform flow, changing velocity across different sections. Now steady flow and unsteady flow. When the fluid properties do not change with respect to time at a particular point, the flow is said to be steady flow. Example, del V by del T is equal to 0. Here in numerator, in uniform flow, it is del X, which represents position, and here it shows del T, which represents time. Example, water flowing from a tank with constant water level. Unsteady flow. When the flow properties changes with time, it is unsteady. dV by dt does not equal to 0. Example, flow when a tap is being operated or closed. So steady flow is particular for a section where discharge is equal dV by dt equal to 0, and for a particular section dV by dt does not equal to 0. Laminar flow and turbulent flow. Fluid particles move in a smooth parallel layers without mixing. This is important. Fluid particles move in a smooth parallel layers without mixing. Such type of flow is known as laminar flow. Usually thick oil with high viscosity usually flow in a laminar way. Mathematically, Reynolds number rho Vd upon mu is less than 2000. Example, slow flow of oil in a pipe. Turbulent flow. Fluid particles move irregularly with mixing and eddies are generated, where Reynolds number is more than 4000. Example is fast flowing of rivers. But between laminar flow and turbulent flow, there is an in-between flow which is known as transition flow. When flow changes from one form to another form, it undergoes transition. That type of flow is known as transition flow, where the Reynolds number is between 2000 to 4000. Here you can very well see in this sketch laminar flow, all layers are moving parallelly to each other. Here there is a slight disturbance in transitional flow, whereas in turbulent flow there is eddies generation. I hope this is clear to you. Compressible flow and incompressible flow. In compressible flow, density remains constant during flow. Rho is constant. Example, water flows in a pipeline. Compressible flow. Density, incompressible flow, where density, in incompressible flow, density remains constant, whereas in compressible flow, density changes significantly during the flow. Example, airflow in jet engines. Another is rotational flow and irrotational flow. Rotational flow, fluid particles rotate about its own axis. Example, whirlpool. Irrotational flow, fluid particles do not rotate about their axis. Example, ideal flow around an aerofoil. In rotational flow, the fluid particle itself rotates around its own axis. Whereas in irrotational flow, fluid particles does not rotate. Angular velocity is zero. Particle is no rotation. One dimensional, two dimensional and three dimensional flow. One dimensional flow, velocity varies in one direction only. In two directional, velocity varies in two direction only. In three directional, velocity varies in three directional flow. The example of one directional flow is flow in a straight pipe. Flow over a plate is the example of two dimensional flow, and airflow around a car, best example of a three dimensional flow. Now what are flow lines? So flow lines are imaginary lines. They are imaginary lines used to represent the motion of fluid particles in a flow field. The main types are path line, streamline, streak line and potential lines, which are also known as equipotential line. So what is a path line? A path line is actual path traced by a single fluid particle over a period of time. If the position of particle is given by x is equal to xt, y is equal to yt and z equal to zt, then this trajectory represents the path line. Therefore, the velocity components are u, v and w, where u is dx by dt, v is dy by dt and w is dz by dt. Example, motion of a leaf in a river, floating in a river. Example, applications are pollutant tracking, particle motion analysis. This is the trajectory of a single particle over the time. Particle moves from here to here to here to here. Streamline. A streamline is drawn in the flow field such that the tangent at any point gives the instantaneous direction of velocity. Fluid particles cannot cross streamline. Remember this. Fluid particles cannot cross streamlines. The equation of the streamline is dx by u is equal to dy by v is equal to dz by w, where u, v and w are velocity components. Example, smooth water flow around a rock. And its applications are aerodynamic design, wind tunnel testing. So lines parallel to flow or the speed of the flow. As you can see, this is a particle, these are streamlines. Streak lines. Streak line is the locus of all fluid particles that have passed through a fixed point. It is formed when particles are continuously released from a point. Example, smoke from a chimney or dye injected in water. Its applications most important is flow visualization experiments. As you can see, if a dye is injected in a flow through a pipe or through a source, through a jet, then path of the particles released from a single point can be tracked. Same is the example of smoke coming out from the chimney. You can track the whole trajectory of that smoke. In steady flow, path line is equal to streamline is equal to streak line. Whereas in unsteady flow, they all are different. Now potential line or equipotential line. It is the line along which velocity potential phi remains constant. It is a line along which velocity potential phi remains constant. So u is equal to del phi by del x, v is equal to del phi by dy, w is equal to del phi by dz. So equipotential lines are always perpendicular to streamlines and exist only in irrotational flow. Equipotential lines are always perpendicular to streamlines and they are only present in irrotational flow. Example is ideal flow around an aerofoil. Application is potential flow theory and groundwater flow analysis. Very important. So these are the lines having constant potentials. Now Reynolds number and Reynolds experiment. So Reynolds number is a dimensionless parameter. It is used to determine the nature of the fluid flow, whether it is laminar, transition or turbulent. We already saw it. It represents the ratio of inertial forces to viscous forces. Mathematical expression is rho Vd upon mu, where rho is density of the fluid, V is mean velocity, D is diameter of the pipe, nu is dynamic viscosity, and kinematic viscosity is given by Vd upon nu. And we already saw it. If Reynolds number is less than 2000, laminar flow is, if Reynolds number is more than 4000, it is turbulent flow, and in between 2000 to 4000, then the flow is transitional flow, means flow is changing from laminar to turbulent, and there are no eddies, but there are irregularities in the parallel surfaces of the flow. Reynolds experiment. Objective: to determine the type of the flow and establish the critical Reynolds number. It was conducted by Osborne Reynolds. Here we can see an experimental setup. A large water tank, horizontal transparent glass pipe, a large water tank, horizontal glass tube, dye injecting device, control valve to regulate the flows, and a measuring tank. Procedure is: water is allowed to flow through the glass pipe, a colored dye is injected from this injector, the behavior of the dye inside the pipe is observed. So this is the injector. Observations, as we saw, RE less than 2000 flow is laminar, more than 4000 flow is turbulent, in between 2000 to 4000 flow is transitional. So conclusion is, Reynolds concluded that the type of the flow depends on the Reynolds number, and the critical Reynolds number for a pipe flow is approximately 2000. Below this value flow is laminar, and we saw that. What are its applications? So design of pipelines, aircraft and automobile design, chemical process industries, water supply systems, biomedical flow analysis. So Reynolds number is a fundamental dimensionless parameter that predicts flow behavior, and Reynolds experiment experimentally demonstrated the transition from laminar to turbulent flow. Now, what is acceleration of fluid particle? So acceleration of the fluid particle may be defined as, it is defined as rather, the rate of change of velocity of fluid particle with respect to time. It is the rate of change of velocity of the fluid particle with respect to time. In fluid flow, velocity may change because of certain reasons like change in time, change in position. Hence, total acceleration consists of two components. Number one, local acceleration, and another is convective acceleration. So local acceleration is the acceleration due to change of velocity with respect to time at a fixed point. dv by dt, local experiment, does not equal to 0 if the flow is unsteady. Example, when a tap is gradually opened, velocity increases with time. This is local acceleration. What is convective acceleration? It is the acceleration due to change in velocity with respect to space, means position or location. It exists even in steady flow if velocity varies along the flow direction. For one-dimensional flow, the convective acceleration is v into del v by del x, where del v by del x does not equal to 0, velocity changes along the distance. Example, water flowing through a converging nozzle where velocity increases as area decreases. Example, used in deriving Euler's equation of motion. It forms the basis of Bernoulli's equation, important in nozzle and diffuser design, used in aerodynamics and pipe flow. Now another is inviscid flow. Now inviscid flow is a type of fluid flow in which viscosity of the fluid particle is assumed to be 0 or negligible. In other words, we can say that there is no internal friction. No internal friction between fluid layers. And because of this, shear stress is 0. No energy loss due to friction. Boundary layer effects are ignored and the flow is governed by Euler's equation instead of Navier's stroke equation. Although all real fluids have some viscosity, the inviscid assumption is used when viscous forces are very small compared to inertial forces. This concept is widely used in aerodynamics and theoretical fluid mechanics to simplify the analysis. This is a small topic. It is an assumption for simplicity of calculations. Velocity potential function. It is a scalar function. It is denoted by phi, used in fluid mechanics to describe fluid flow, especially irrotational flow. So velocity potential function is defined such that the velocity components of the fluids are equal to spatial derivatives of phi. For a three-dimensional flow, u is del phi by del x, v is equal to del phi by del y, and w is del phi by del z, where u, e and w are velocity components in x, y and z directions. Phi is velocity potential function. What is the physical significance? The velocity at any point is obtained from the gradient phi. Surfaces of constant phi are called as equipotential surfaces. Flow always occurs perpendicular to equipotential surfaces. The applications are potential flow theory, analysis of flow around aerofoils, flow past cylinders and spheres, aerodynamics and hydrodynamic problems. Advantages: simplifies the complex fluid flow problems, reduces vector equations to scalar form, and useful in theoretical fluid mechanics. Stream function. The stream function is a scalar function denoted by psi, psi psi. This is the notation psi. It is used to describe two-dimensional incompressible flow. For a 2D flow in x and y directions, the velocity components are defined as u is equal to del psi by del y, v is equal to negative of del psi by del x, where u is velocity in x direction, v is velocity in y direction, psi is stream function. The physical meaning is the value of the stream function represents flow rate per unit depth. Difference between two stream function values gives the discharge between two streamlines. Lines of constant psi are called as streamlines, and fluid particles always move along the streamlines. Conditional for existence. It automatically satisfies the equation of continuity, that is del u by del x plus del v by del y is equal to 0, and relation between stream function and velocity function. If both velocity function phi and stream function psi exist, the flow is irrotational and incompressible. It satisfies the Cauchy-Riemann equation. Streamlines and equipotential lines are orthogonal to each other, means perpendicular. Again, its applications are potential flow analysis, flow around cylinders and airfoils, aerodynamics and hydrodynamics, and solving fluid problems graphically. It reduces two velocity components into one function, simplifies analysis of incompressible flow, and useful for visualizing fluids in motion. Equipotential lines. It is a line along which velocity potential phi remains constant throughout. So phi is constant. It is used in potential flow theory to describe fluid motion. Physical meaning: no fluid flows along equipotential lines. Fluid motion crosses equipotential lines at right angles, and it represents the location of potential energy per unit mass. Mathematical expression is d phi is equal to 0. Then the line represents an equipotential line. For incompressible and irrotational flow, the velocity potential satisfies this Laplace equation. Now the relation: if both velocity potential and stream function exist, equipotential line is constant, stream lines are constant, and they are mutually perpendicular. Again, same applications: flow around cylinders, flow past aerofoils, groundwater flow analysis, electrostatics. Advantages: helps to visualize fluid flow, simplifies mathematical analysis, and used in solving Laplace equation graphically. So, an equipotential line is a line in which The fluid flow field where velocity potential remains constant. Fluid flows perpendicular to these lines and they are always orthogonal to streamlines in irrotational flow. Flow net. So a flow net is a graphical representation used in fluid mechanics to study the flow of fluids through porous media like soil. It consists of two sets, flow lines, we can say streamlines, and equipotential lines, that is phi. These two families of lines always intersect each other at 90 degree. So these are equipotential lines C1, C2, C3, C4, phi, and streamlines are psi is equal to C1, C2, C3, and they intersect each other at right angles. Most importantly, they are used for groundwater flow analysis. This is an AI generated image, water flowing through porous soils. This is an impervious layer. Psi is flow lines or path of fluid flow. Phi is equipotential lines, lines of equal hydraulic head. So what is flow net? What are the characteristics? They are orthogonality is the characteristics, means flow lines and equipotential lines intersect at 90 degrees. Curvilinear squares. Squares are not perfect but close. No intersection with same family. Flow lines never cross other flow lines. Flow lines never cross with other flow lines. The drop in the hydraulic head between successive equipotential lines is constant, equal discharge in flow channels and smooth curves, no sharp bends. Uses of flow nets in geotechnical and hydraulic engineering. Seepage analysis helps to calculate rate of seepage through soil. Uplift pressure estimation determines pressure acting beneath the structures like dams or retaining walls. Used for designing of hydraulic structures like earthen dams, sheet piles, canal lining. Determination of hydraulic gradient means helps in risk assessment of piping or soil erosion, and helps in study of flow patterns. It helps in visualization that how water moves beneath the soil layers. Now, what are the methods for making a flow net or for construction of flow nets? Its working principle, the basic procedures or the ideas, its advantages and limitations. So basically there are 5 methods. One is analytical method, another is graphical method, electrical analogy method, relaxation method, and Heli-Shaw apparatus. So analytical method, it is based on Laplace equation governing steady seepage flow. The basic idea is solving differential equations using boundary conditions to obtain flow lines and equipotential lines mathematically. Accuracy, very high accuracy. Theoretically sound, no approximation errors. Limitations, very complex mathematics, difficult for irregular boundaries, and not practical for field problems. Graphical method, based on orthogonal relationships, means 90-degree relationships between flow lines and equipotential lines, 90 degrees. Draws flow net manually by trial and error, ensuring curvilinear squares and 90-degree intersections, which is simple and widely used. No advanced tools required. Suitable for most of the practical problems. Accuracy depends on skill, time consuming, and prone to drawing errors. Electrical analogy method. Analogy between fluid flow and electric current, both follow Laplace equation. It uses conductive sheet, application of voltage, measurement of equipotential lines, and drawing of flow lines perpendicular to them. Good for complex geometrics. More accurate than graphical method. Experimental validation is possible. Requires special equipment, time consuming setup, largely replaced by computational or computer methods. Relaxation method. Numerical solution of Laplace equation using finite difference approximation. Divide domain into grid. Iterative, adjusting the head values until equilibrium is reached. Suitable for complex problems. forms basis for computer simulations. Manually very tedious, requires high number of iterations. There is possibility of errors if proper convergence is not achieved. Helio apparatus. Flow between closely spaced plates simulates the flow through porous media using Helio apparatus. Use viscous fluids between plates. Inject dye to visualize flow lines and equipotential lines. It is used for visual understanding and very easy to understand. Basically, it is a demonstration. It is used for demonstrating and teaching tools. Experimental errors are possible. Limited practical applications. So flow nets in fluid mechanics have several key limitations. They work best under ideal conditions. Means flow is homogeneous and isotropic, not suitable for complex soils like layered or anisotropic media. Accuracy depends on careful graphical drawing, making them prone to errors, and process can be time consuming. Additionally, they cannot be used for unsteady or time dependent flow. I hope you enjoyed this session, and we will be meeting with another lecture going in depth with another topic including Bernoulli's equation and many more. Thank you so much. Have a nice day.